Hello and welcome to Pharma-info Shubhashish. Now let us just straightway take this topic, that is synthesis of pyridine, right? So in our earlier video, right, I was discussing about this the overview as well as the basicity of pyridine. Now this time it's synthesis of pyridine. This is as per PCI syllabus, and this is there in POC 3, that is Pharmaceutical Organic Chemistry 3. Now coming to synthesis of pyridine, we all know that pyridine is something like this. It was talked, or it was discussed, illustrated rather, in my last meeting or last talk. So this is about your pyridine. Now how this can be synthesized, right? So there are various ways by which pyridine was synthesized actually. So now let us just deal with the first one, right? In the first synthesis, what you observe, that first thing is that this is the one that we need to make, right? Now it comprises of what? It comprises of this kind of backbone, right? So this is found to be the backbone of pyridine. Now if I want to see this one, right, I can at least figure out, or rather we can say that it's a combination of three different reagents, or rather out of those three, two are found to be similar and one is found to be different, right? If I just condense them, or rather if I just put them in a red hot tube, what will happen? They will cyclized and provide you what? The pyridine. So how this can be done actually? As I said, we have to introduce what? A combination of two different reagents, right? So how this can be made with this backbone? The first thing is that I can do it like this, I can even do it like this, and this can be done like this. So here we have three different fragments, what we can say. If I just complete the fragments, right, two are found to be similar. As I said, that it must be a combination of two reagent, right? Two reagent and reagents. So one reagent seems to be appearing multiple times, so this one is the one that should appear multiple times. So this is nothing but acetylene, right? Acetylene, and this one is what? If I just complete this one, it turns out to be hydrogen cyanide, right? So this one is hydrogen cyanide, and the other one is acetylene. So we need what? We need two molecules of acetylene, that is C2H2, and we need one molecule of HCN, right? We need one molecule of HCN. All you need to do is that this combination need to be passed through a red hot tube, right? A red hot tube, and after spending within the tube for a considerable period of time, what will happen? The cyclization occurs, and it is the cyclization that eventually give rise to the making of, or the production of what? Pyridine. So this is the first way of making pyridine. So here what we did actually, two molecules of acetylene, two molecules of acetylene, when they reacted with one molecule of HCN, and this combination, while being passed through a red hot tube, spending a lot of time, quality times within the red hot tube, right? What will happen? At the end of that particular period, what we observed, that cyclization took place, and finally we got what? Pyridine. So this is the first way of making pyridine, right? The second way, the second way is not meant for making only unsubstituted pyridine, rather it is basically proposed to make substituted pyridine, right? And this was proposed by the scientist called Hans, Hantzsch. So Hans, he is the scientist, right, who basically developed a way by which pyridine can be synthesized, and that pyridine is not found to be a unsubstituted one, it's a substituted one. So how this can be done actually? Now the one which we are going to make, it is somewhat like this, right? Let me just see that what is the one that we are after. We are going to make pyridine, and that too a substituted pyridine. So this is found to be the final product obtained when Hans underwent this kind of synthesis and all, right? So this is pyridine, and this is tri-substituted pyridine. So what are the locations? 1, 2, 3, 4, 5, 6. So 3 methyl groups which are placed at 2nd position, 4th position, as well as 6th positions, right? And all are found to be methyl. So here we have 2, 4, 6 trimethyl pyridine. So this is the one that we are going to make. Now how this can be made actually? So if I just see the structure, right? If I just see the structure, then I need to find the zone which are found to be very soft zone. That means isolating those zones, and finally again we'll just combining the zones, right, which may lead to the production of this particular compound. All I wanted to say is, if I just, because after all this is found to be, this is the compound which is nothing but a suitable combination of various fragments, right? So now first we need to find out that what are the different fragments which will eventually give rise to the production of what? 2,4,6 trimethyl pyridine, right? So if I, in that very process, what am I supposed to do actually? I'm just trying to segregate the entire structure into three different portions, right? And in that three different portions, this is found to be the first one, right? And the second one is found to be more or less similar actually. These two are found to be similar, and finally we have a nitrogen, right? So if I just try to segregate the entire compounds, all I get is 4 different fragments, right? So 4 different zones, 2 are found to be identical and 2 are found to be different, right? Chalo. So now how this can be made actually? Now what are the possible fragments that we came to know right now? And now upon completion of those fragments, at least we can get to know about the starting materials or the various reagents which constitute this particular structure, right? So now in that very process of making this tri-substituted pyridine, Hans initially took what? A diketoester, right? Now which is the diketoester? Diketoester means the one in which 2 keto moiety is there. One is found to be the keto of an ester, the other one keto is found to be a solo keto, right? So if I just see the general form of an ester, it is somewhat like this: R, C, double bond O, O, R prime. So this is found to be the general form of an ester. That means alkyl alkanoate, right? Now in that alkyl alkanoate, only one keto is there, and that is found to be the part of an ester, right? So now, but here we need to start up the process with diketoester. So now in diketoester, of course, obviously, in addition to this keto from that ester, you must introduce what? Another keto group, right? So how this will be actually? So if the keto has to be inserted, that must be a part of this R, right? So in that case, what can be done here is, so this is found to be the acetyl, right? Now acetyl is the one in which one keto moiety is there, and followed by we have a, so after immediate next to this acetyl, we need to put one CH2, that is found to be a part of the alkanoate portion, right? And then we have another C double bond O followed by O and R prime. R prime, okay, let me do one thing. The R is nothing but a C2H5, right? So thus we got what? This diketoester, and diketoester is nothing but what we can say is it is ethyl acetoacetate. So the name of this diketoester is ethyl acetoacetate. Right. So this is found to be the one, okay, which need to appear multiple times, which we are going to introduce multiple times, because these two are the fragments which are found to be similar, or right, they born out of similar compounds. So that is why this is the one which may give us what? These two fragments, right? So we are left with 2 more. One is found to be the top one, which is having 2 carbon, and the other one is found to be a solo nitrogen, right? Now let's do one thing. Let us just see that okay, they could become what? Okay, this is the one, okay, which may be there is a chance that, okay, fine, if I just deal with 2 carbon, this is found to be the backbone of the top one, right? If this is found to be the backbone, so how this can be a part of the final compound actually? So this can be given the shape like this, right? This can be given the shape like this. So thus we got another we developed another compound from the fragment, that is your acetaldehyde. So the first one is ethyl acetoacetate, the second one is acetaldehyde. Now at here at the bottom, what we have, we are left with what? The nitrogen. As I am going to incorporate the nitrogen in a cyclic system, so the preferred way of or the shape which can be given to this nitrogen is nothing but ammonia, right? Ammonia. So now with that we are done with what? The 3 different reagents, right? Or 3 different reagents which may part or which should take part, okay, in the final making of this particular compound, right? So now let's do one thing. Let us just see that how the reaction can proceed. So here we go with these 3 reagents, right? So let me do one thing. Let me just first orient these 3 compounds in such a way so that at least we are tending towards the final compound, right? So now this is the one, the diketo compound. Let me tell you one thing. It is having the potential to transform itself into another tautomers, right? So if I say tautomers, that means the isomers which are in dynamic equilibrium. So sometimes you might have heard about keto as well as enol tautomers, right? So at this very moment we are dealing with the keto compound, right? It is the keto compound if it's having that element to transform itself into an enol form, right? So it can readily get converted to an enol form, right? So now the thing is that, so how this can transform itself? Let us just see that one first. So now if I just orient this one in this way, like H5C2O C double bond O, and then followed by we have a CH2 here, then we have a C double bond O here and CH3 over here, right? So what can be done here is this keto group is trying to change its form from keto to enol, right? In that very process, what it is supposed to do actually. So this is just trying to take one hydrogen from its neighbor, and this hydrogen should be inserted over here, and in that very process this double bond will get broken, or rather it will shift its position from here to here. So if I just change it, how this, so this can acquire this kind of form. So in that very process what will happen, this will get omitted, and finally we can get like this, right? So this is the thing. So earlier it was keto, later on it has been converted to CH double bond COH, right? So this is a kind of beta hydroxy, what we can say, because this is found to be the alpha position, this one is the beta position, and at this beta position we have a hydroxy group. So it is basically a beta hydroxy ester, what we can say, right? So the same thing happened to the other atom as well, or other molecule as well, because as we are taking two molecules of this beta keto ester, the same fate for the other compound as well. So here what we can do this, we can just reorient this in this way, right? Chalo. So now we have placed them parallelly, what we can say. Now on top of it, what am I supposed to bring? I am supposed to keep what? The acetaldehyde, and that too in this way actually. Okay, fine. Now beneath this I need to place what? The hydrogen, right? Of this nitrogen along with the hydrogens, right? So this is the thing. So now we have with us two molecules of this beta hydroxy ester, one molecule of acetaldehyde, the other molecule of ammonia, right? Now if I just try to place them in this way, what will happen, and just ask them to condense, so they will eventually give rise to the making of H5C2O, C double bond O, then followed by CH. We have another carbon over here, on top of it we have CH3, and then we have something of that sort, HC, then C double bond O, then C2H5, and then we have another C. So here we have methyl, we have a double bond over here, we have NH here, we have double bond here, we have carbon here, and we have something of that sort, right? So it turns out to be a pyridine kind of. That means it's not a pyridine, rather it's a semi-pyridine, where the aromaticity has not yet been complied actually, right? So it has not been complied yet. So now what exactly need to be done here? So since it is not in pyridine, rather in a pipyridine state, so it's an intermediate between pyridine and pipyridine, what we can say, right? Because pipyridine is the one in which NH is there. So now that this hydrogen need to be removed, because all am I supposed to do is I need to incorporate 6 pi electrons here. Now still it is deficient with 2 more electrons that need to be incorporated. So best way is to just oxidize it, because I need to remove this hydrogen, and in the very process what am I supposed to do? I am supposed to perform an oxidation process, right? So in that very process of oxidation, the reagent which I am trying to take is concentrated HNO3, right? So what this concentrated HNO3 will do actually, the concentrated HNO3 will basically reduce, oxidize this one, and in that very process of oxidation the hydrogen will get removed, right? So what is left in the process? This is the one which is left in the process, right? We have a carbon followed by a methyl, then we have this hydrogen should not be there actually. So we have a methyl over here, then nitrogen, then carbon, we have a double bond carbon again. So here we have C double bond O, then C2H5, right? C2H5, and then something like this, right? So now this can be placed in this way. The pi bonds can be placed in an alternate way, because they must be in a conjugated fashion. So that is why this is something of that sort, right? That is getting formed here, right? So now the thing is that, so here we are almost done with the making and all, right? Now what is left in the process? Only thing that is left in the process is removal of this ester, because our final compound is not found to be esterified pyridine, rather we are after what? Trimethyl pyridine, and that too they are placed at 2nd, 4th as well as 6th position, right? So what could be done to this particular compound so that the esteric form or the ester moiety will get removed actually? So here we are supposed to treat this one with calcium oxide, and calcium oxide will respond only in presence of what? In presence of a base, that means OH minus. That is your choice whether you are going to take potassium hydroxide or sodium hydroxide, but anyway, calcium hydroxide while being used, right, make sure that for the purpose of removing the esteric moiety, make sure that the calcium oxide should be amalgamated or mixed with what, a base, right? So here either you can take potassium or we can take sodium, right? These two are the choices, right? Now what will happen here? So while treating this with that, this combination, so what will happen? It ultimately leads to the formation of what? The pyridine that we are after actually, that is trimethyl pyridine. So this is how we have got what, the compound of interest, that is trimethyl pyridine. So what happened here initially? Let us just do one, just recap that one, fine. So recapitulate that one, fine. So this is the ester, we have an aldehyde, we have an ammonia, right? These three while being condensed, what will happen? Initially there is a formation of partially saturated pyridine, of course substituted pyridine, so in which the unwanted stuff is found to be the esteric moiety, and moreover since it's a partially saturated, so that is why we need to make it aromatic. For that we just treated this one with concentrated HNO3. What this is meant for, what this was meant for, removing the hydrogen and making this pyridine, fine. So this is found to be the semi product rather, or semi-formed product rather. Now this product while being treated with calcium oxide in presence of sodium hydroxide or potassium hydroxide, which ultimately resulted in the formation of what? The pyridine, that is 2,6,5,2,46 trimethyl pyridine. So hence we are done with what? So here we are almost done with the making of pyridine. So we have one more synthesis actually. So these two are found to be the one which is found to be highly frequently being used, right? So that's all for this synthesis of pyridine. Now in my next video, definitely I'll talk with related to this synthesis, not synthesis, rather the reactions of pyridine, right? So various reactions of pyridine, because right now it's not the because reactions of pyridine, it requires more time because several reactions are there, and moreover the fundamentals need to be discussed while performing whether it's an electrophilic or nucleophilic aromatic substitution. So as the fundamentals are there, so that is why I am not illustrating or stretching this one, okay, because it will take another half an hour. So it will be better for me to just stop here and just in the next part of this pyridine, okay, let me just bring it, this means bring the various reactions of pyridine and subsequently the medicinal uses of pyridine derivatives. So hope you have enjoyed, or rather understood the in detail explanation of this making of pyridines, right? So if you like my channel, please do subscribe, as well as please put your valuable comments in the comment box. So see you in my next video. Thank you.